Good morning all of you. My name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education to all. For that purpose I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, we are discussing about the stability theory, in which we have discussed that bounded input bounded output criteria is one of the essential parameter for checking the stability of any system. We have also discussed that stability could be analyzed in two parts. Number one is your absolute stability and second one is your relative stability. So we have also discussed that for absolute stability criteria, we have introduced the concept of Raoult-Hurwitz criteria, which is basically the extension of polynomial theory. It is basically the application of polynomial theory in characterization of stability analysis of any system. These are the outlines that we have already discussed in our earlier lecture. We have introduced the concept of stability, where we have mentioned that positioning of poles plays a vital role while characterization of the stability of the system. Then we have discussed Raoult-Hurwitz stability criteria. We have also discussed how we're going to generate a basic Raoult table and how we're going to manipulate that table in order to characterize whether the given system is a stable one or unstable one. We have also discussed some of the examples. We have seen that the number of sign changes in the elements of the first column of the Raoult table gives the idea about the stability of the system. If there is no sign change occurs in the first column of the Raoult table, then the system will be a stable one. If there exists certain number of sign changes, then that much number of poles will going to lie in the right side of the S-plane. So now in this particular lecture, we'll discuss about various special cases of Raoult array that we're going to encounter while creating Raoult array. Then at last we'll discuss about various applications of Raoult-Hurwitz criteria. So we'll start up with special cases of Raoult array. First one is case of a 0 in the first column. So when we are trying to create Raoult table for any given polynomial, suppose we encounter a 0 in the first column, then how we're going to encounter that? Just because due to that 0th element, when we're going to evaluate the next element of the Raoult table, obviously in the first column, then it will become divide by 0 form, something divide by 0 form, which will going to make our Raoult array element makes it into infinity. So how are you going to encounter that? So for example, let us say we'll going to take this polynomial s cube plus 2s square plus s plus 2. So when we're going to create the Raoult table, we're left with s cube and s square. The coefficient of s cube is 1. Then after excluding second coefficient of s square, we'll be having this again 1. Then the coefficient of s square is 2. Then after excluding next coefficient, we'll be having this 2. So 2 1 ja 2 minus 2 1 ja 2 divided by 2, that turns out to be 0. How will we going to complete our Raoult table? Just because when we're going to evaluate the next value of Raoult array, we'll be going to have divide by 0 format. I mean 0 cross 2 minus 2 cross 0 divide by 0. So it will become indeterminate form. So how are we going to encounter? This actually presents a problem when we come to obtain the fourth row divide by 0. So this problem can be solved by two methods. Number one is your epsilon method and second one is your reverse coefficient method. So we'll take up one by one. So here is your first remedy, how we're going to encounter 0 in the first column of the Raoult table. We're going to define a small positive number epsilon and evaluate the whole array as we did earlier. So in place of 0, we have put this epsilon, which is a very small positive quantity, and when we're going to evaluate next value, it will become epsilon into 2 minus 2 times of 0 divided by epsilon. So we are left with again 2. So this actually covers up the complete Routh array. Here one point should be noted very clearly. If the element above and below the epsilon in the first column have the same sign, I mean just like this +2 and +2, they'll be having same sign, then a pair of imaginary root is indicated. Obviously, if we analyze this first column of Routh array, plus again epsilon is a small positive quantity, again positive sign, then 2 again a positive quantity. So there is no sign change in the first column of Routh array, hence the system is stable. But just because the just above and below elements are of same sign, then it actually indicates that we'll be having a pair of imaginary root. So let us understand this particular rule with another example. This is actually a good question which has been, I think, asked in GATE examination too. So we'll try to solve this problem. Determine the stability of the following system whose transfer function is given to us as 10 by s to the power 5 plus 2s4 plus 3s3 plus 6s square plus 5s plus 3. Now let us try to evaluate the Routh table for this particular transfer function. So here is the Routh table. Again, create the Routh table associated with this particular transfer function. We're going to write up the coefficients of various powers of s. So first two rows we have to write up as it is, s to the power 5 and then s to the power 4. The coefficient of s to the power 5 is 1. Then after leaving the coefficient of second term, we'll be having 3. Then after leaving 6, we'll be having 5. Then the coefficient of s to the power 4 is 2. Then after leaving this 3, we'll be having this 6 and then 3. So 2 3s are 6 minus 6 divided by 2 turns out to be 0. And then again 2 5s are 10 minus 3 divided by 2, that are left with 7 by 2. Again next term is 0. So here we are trying to solve this particular problem with epsilon method, as the third element in the first column of the Routh array is 0. So we're going to cut it out, this 0, and use this epsilon and just try to solve the Routh array. So again epsilon into 6 minus 7 by 2 into 2 by epsilon. We are left with 6 epsilon minus 7 by epsilon. Then this epsilon into 3 minus 2 times of 0 divided by epsilon, that leaves us with 3. Similarly, we are going to evaluate next value of Routh array. 6 epsilon minus 7 by epsilon multiplied by 7 by 2 minus 3 epsilon divided by same this material. So we are left with 42 epsilon minus 49 minus 6 epsilon square divided by 12 epsilon minus 14. And similarly this particular element into 3 minus 0 divided by this whole element, we are left with 3 only. So this automatically completes the Routh array of this transfer function. So now next step is to check or analyze the first column of the Routh array. So here we'll have to focus all those elements about the sign changes, or what are the various signs. So if we're going to assume epsilon as a positive quantity, then this 1 is your positive, 2 is again positive, epsilon again is positive, 6 epsilon minus 7. Since epsilon is very small positive quantity, so obviously 7 is greater than 6 epsilon. So outcome will be a negative quantity. If we're going to consider this particular equation, then 42 epsilon minus 49 minus epsilon square, this will be a negative quantity, and 12 epsilon minus 14, this will also be a negative quantity. So negative by negative, that turns out to be a positive quantity. Then 3 is again positive. Similarly, if we're going to consider that epsilon is a small negative quantity, actually we can assume epsilon whether it is a small positive quantity or a small negative quantity, then correspondingly we're going to analyze how we're going to analyze the Routh table. So just to avoid various sort of confusion, let us assume that epsilon is a small positive quantity, and from now onwards we'll perform all our calculation while considering epsilon is a small positive quantity. So while analyzing the various sign changes, first value to second value, positive, no sign change, then again positive to positive, again no sign change, positive to negative, one sign change, then again negative to positive, second sign change, and then again positive to positive, that is no sign change. So there exist actually two sign changes. Since two sign changes are there, hence the system is unstable, and it actually indicates that two poles lies in the right hand side of the S-plane. So again, case of 0 in the first column, remedy 2, second method, analyzing stability via reverse coefficient method. So a polynomial that has the reciprocal roots of the original polynomial has its roots distributed the same right half plane, left half plane or imaginary axis, because taking the reciprocal of the roots value does not move it into the another region. What we wanted to say in this particular point is, suppose the root of polynomial is 2. So if we're going to take the reciprocal of 2, again it will become 1 by 2, which is equal to 0.5, which is your same positive value. Anyhow, it will not going to become any negative value. So point is, suppose a root lie in the right half of the S-plane, then the reciprocal of its root will also going to lie on the right side of the S-plane. It will not going to change its position. If we can find the polynomial that has the reciprocal roots of the original, it is possible that the route table for the new polynomial will not have the 0 in the first column. If we are going to use this particular method, then this will not always be the case, that we'll again going to get the same 0 in the first column of the route table as we get the earlier one. So the polynomials with the reciprocal roots is the polynomial with the coefficients written in the reverse order. So if we want to find out the polynomial which is having the reciprocal roots, we'll simply going to write down the coefficient in the reverse manner or reverse order. This method is usually easier in terms of computation than the epsilon method. So again, we'll try to encounter same problem with this second method, reverse coefficient method, and try to check out the stability of the system, whether we'll get the same answer or not. Same transfer function, which has been written as 10 upon s to the power 5 plus 2s4 plus 3s cube plus 6s square plus 5s plus 3. So route table through reverse coefficient method turns out to be, since this is the transfer function, s to the power 5, 2s4 plus 3s cube plus 6s square plus 5s plus 3. Now we're going to simply inverting the coefficients of this particular polynomial. For s to the power 5, we'll be having 3. Then again, after skipping this 5, we'll be having 6. Then after skipping next polynomial, we'll be having 2. So the next polynomial coefficient will be having 2. Then the coefficient of s to the power 4, we're going to write 5. Then after skipping this 6, we're going to write this 3. Then after skipping 2, we're going to write as 1. And now we'll try to follow the same steps in order to calculate the Routh array. So this element turns out to be 5 6 are 30 minus 3 3 are 9 divided by 5, which left with 4.2. Then similarly, next value 5 2 are 10 minus 3 1 are 3 divided by 5, that turns out to be 1.4. So in our earlier case, we have seen that we'll be having a 0 at this particular position, which is not be the case while we are using this reverse coefficient method. So now we're going to compute this whole route table as we usually used to do so. Again, 4.2 minus 3 minus 5 times of 1.4 divided by 4 times 2. We are left with 1.33. So after following the same steps that we have taken earlier, we're going to complete this Routh table. So now next step is to analyze the stability of the system. We'll again going to analyze this first column of the Routh table. So we're going to evaluate the number of sign changes. Plus 2 plus no sign change, again plus 2 plus, no sign change, plus 2 plus, again no sign change, then plus 2 minus, 1 sign change, and then again minus 2 plus another sign change. So there exist two sign changes. Since there exist two sign changes in the first column of the Routh array, it shows that we'll be having two poles existing in the right half of the S plane. So since two sign changes, hence the system is unstable and the two poles lies in the right hand side of the S plane. So this table does not have a 0 in the first column. In both the cases the result is same. So point is, if we'll be having a 0 that exists in the first column of the Routh array, then we can solve it by two methods. Number one is your epsilon and second one is your reverse coefficient methods. So now another special case is case of rows of zeros. We'll simply going to call it as R of Z or rows of zeros. So while making a Routh table, we may find that an entire row consists of zeros. For example, let us consider this particular polynomial s to the power 5 plus 2s4 plus 24s cube plus 48s square minus 25s minus 50. So let us try to evaluate the Routh table for this particular polynomial. So we're going to write up the coefficients s to the power 5, s to the power 4, s to the power 3, s square, and again so on. So the coefficient of s to the power 5 is 1, then after skipping this second we'll be having the coefficient is 24, after skipping 48 we'll be having the coefficient minus 25. Then coefficient of s to the power 4 is 2, then after skipping 24 we'll be having 48, then after skipping minus 25 we'll be having minus 50. So how are we going to evaluate the third row? 2 times of 24, that is 48, minus 48 into 1, 48 divided by 2, 0 by 2 turns out to be 0. Then 2 into minus 25 is equal to minus 50, minus times of minus 50 into 1, that is plus 50, divided by 2, again that turns out to be 0. So if we're going to observe this particular row, this complete row will be a 0, and we'll try to calculate the next element, all will become divided by 0 form. So how we're going to encounter this sort of problem, we'll try to analyze it. So just above the row in which we have find complete 0, next above row is the coefficient of this next above row is 2, 48 and minus 50. We'll try to make an polynomial equation with these coefficients. So that equation turns out to be 2 times of s to the power 4 plus 48 times of s square minus 50, that is equal to 0. This particular formed equation is actually known as the auxiliary equation. So let us denote this auxiliary equation as P of s. P of s turns out to be 2s4 plus 48s square minus 50 is equal to 0. We'll simply going to take the derivative of this auxiliary equation and we have to evaluate P prime of s. That turns out to be 4 to the 8 times of s cube plus 96s, that is equal to 0. So now we're going to take this particular polynomial equation in s cube and s, and we're going to use these coefficients 8 and 96 to complete our Routh table. So what we're going to do is we will have to replace the row with the coefficients of P prime of s. So since we have seen that the coefficient of s cube will be having a complete 0, so we're going to replace that zeros with the coefficients of auxiliary equations derivative, that is your 8 and 96, and then we again try to complete this Routh table with these 8 and 96. So next element turns out to be 8 times of 48 minus 96 into 2 divided by 8 turns out to be 24. Then again 8 times of minus 50 minus 2 times of 0 divided by 8 turns out to be 96. So similarly we are going to complete our Routh table as we did earlier. So now in order to check the stability of the given system's transfer function or for the given polynomial, we are going to analyze the first column of the Routh table. So we'll basically try to find out the number of sign changes in the first column of the Routh table. Again plus 1 to plus 2, again positive, no sign change. Then from 2 to 8, again positive, there is no sign change. then plus 8 to 24, again no sign change, positive. 24 to 112.7, again positive, no sign change. Then 112.7 to minus 50, there is one sign change. So it actually shows that the system is unstable and there exists one poles that lie in the right side of the S-plane. It is having a one root which is having positive real part. So in case of zeros, an entire row of zeros will appear in the route table when a purely even or purely odd polynomial is the factor of the original polynomial. This thing has to be noted very carefully, that if in any polynomial while creating the route table an entire row becomes 0, it actually indicates whether a pure even or pure odd polynomial is the factor of that original polynomial. Even polynomial only have roots that are symmetrical about the origin. So this symmetry can occur under three conditions of the root positions. I mean, if this condition is existent, then it will always be the case that the roots will be symmetrical about the origin. So this symmetry could occur by three types. First one, if eighth portion is the roots are symmetrical and real. Second is the roots are symmetrical and imaginary, and the third case that is possible is the roots are quadrantal. So how are you going to check out the symmetry about the origin? This particular figure shows that thing. So in our first case, we have said that roots are real but they are symmetrical about origin. So this A and A actually shows that roots are real but they are symmetrical about the origin. Second, in case of B, roots are imaginary but they are also symmetrical to the origin. Then this particular position B and B actually shows the second case, and roots are symmetrical about the origin. So third case is, but they are quadrilateral. This C and this C and C actually shows the symmetricity about the origin. So this particular figure actually shows the root position to generate even polynomial. So the rows of 0 tells us the existence of an even polynomial whose roots are symmetrical about the origin, as we have seen in our last figure. Some of these roots could be on j omega axis. As j omega axis roots are symmetric about the origin, and if we do not have a row of zeros, then we can conclude that we cannot possibly have the j omega roots. So it means if we'll be having a zeros rows, it clearly indicates that we'll be having some roots on j omega axis. If we do not have any complete zero rows, then we possibly cannot have the roots on the j omega axis. Let us understand in a much more better manner with some example. So let us take a quick question. Determine the number of right half plane poles in the closed loop transfer function, which is being given as 10 by s to the power 5 plus 7s to the power 4 plus 6s cube plus 42s square plus 8s plus 56. So the closed loop transfer function of any system is given to you by this equation. So we have to calculate how many number of poles are actually lying in the right hand side of the S-plane. So the characteristic equation of this particular transfer function is the denominator polynomial. So we'll try to evaluate the route table for this given polynomial, that is s to the power 5 and s to the power 4. Again we will going to write up the coefficients 1, 6 and 8, then 7, 42 and 56. While studying Routh-Hurwitz criteria, we had also mentioned that for the simplicity, for the sake of easier manipulation or calculating various elements of route table, we can simply divide or multiply with any constant term. So in the second row we are going to divide by 7, then we are left with 1, 7 6 are 42, 6 and 7 8 are 56. So we'll again going to evaluate the route table. Again 1 times of 6 minus 6 into 1, again this element turns out to be 0. 1 times of 8 minus 8 times of 1, again second element is also equal to 0. So this will become the complete 0 row. So we're going to take up the auxiliary equation s to the power 4 plus 6s square plus 8 is equal to 0. Then we're going to evaluate this complete route table. 4s cube plus 12s, again 12 is the coefficient and this coefficient is 0. So we are left with 1, 3 and 0. This is actually the coefficients of auxiliary equation. Then we're going to complete our route table with this auxiliary equations coefficient. So again 1 times of 6 minus 3 times of 1 divided by 1 turns out to be 3. 1 times of 8 minus 1 times of 0, again that turns out to be 8. Then next 3 into 3, 9 minus 8 divided by 3, that is equal to 1 by 3, again that is equal to 0. 1 by 3 into 8 minus 0 divided by 1 by 3, that again turns out to be 8. So now in order to check out number of poles that are existing in the right side of the S-plane, we are going to analyze the first column of the route table. So plus 1, 2, plus 1, no sign change. Again plus 1, 2, plus 1, again no sign change. Then plus 1, 2, plus 3, both are positive quantities, again no sign change. Then 3 to 1 by 3, again both are positive quantity, means again no sign change. 1 by 3 to 8, again positive, means there is no sign change. Hence we could say that there will be no pole that is lying on the right hand side of the S-plane, or we could say there are 0 number of poles which are lying in the right hand side of the S-plane. Conversely, we can conclude that this particular system is a stable one. Route table shows that all entries in the first column are positive, hence there are no right half plane poles. Then another special case is case of repeated roots of the characteristic equation on the j omega axis. So suppose there exist repeated roots of the characteristic equation. So if the j omega roots are repeated, the system response will be unstable and it is with the form of t times of sine of omega t minus phi. And with the help of route criteria, we cannot reveal this sort of instability. I mean, we could not predict whether the system is a stable one or unstable one. So in order to find out whether whether this particular system is a stable one or unstable one, we are only option left with, we have to evaluate all the roots of the characteristic equation separately, and after finding those roots explicitly, we can comment on the system's stability. If certain poles will be having positive real parts, then our system will become unstable one, and if we do not find any roots of the characteristics equation with positive real parts, then our system will be a stable system. So let us quickly understand it with a small simpler example. Let us assume the characteristic equation as q of s is equal to s to the power 5 plus s to the power 4 plus 4s cube plus 24s square plus 3s plus 63, and we will actually try to evaluate the route table. S to the power 5, s to the power 4, we are going to write up the coefficients. The coefficient of s to the power 5 is 1, again skipping this s to the power 4 coefficient, we will be having 4. Then again skipping the coefficient of s square, we will be having 3. Then the coefficient of s to the power 4 is 1, again skipping next coefficient, we will be having 24. And then again skipping next coefficient, we will be having 63. So 1 times of 4 minus 24 into 1 divided by 1, that turns out to be minus 20. 1 into 3 minus 63 into 1 divided by 1, that turns out to be minus 60. So again, after evaluating the route table, then when we are going to evaluate this row, we will be having 21 into minus 60 minus 63 into 20, again 0, 21 into 0 minus 20 into 0, again 0. This complete whole row will be a 0th row. What we are going to do now? We are going to take up this auxiliary equation, 21s square plus 63 is equal to 0. So the auxiliary equation or auxiliary polynomial u of s turns out to be 21s square plus 63 is equal to 21 times of s square plus 3. So after solving this, we are left with s plus j root 3 into s minus j root 3, which indicates that two roots are on the imaginary j omega axis, plus minus j root 3. So to examine the remaining roots, we are going to divide the characteristic equation q of s with this auxiliary polynomial whose roots we have actually evaluated. So qs by s square plus 3, we are left with sq plus s square plus s plus 21. Let us suppose that this particular equation is your A. So now in order to get the complete solution or complete factors of this characteristic equation, we have to find out the factors of this equation. We have already found out that the two roots of the given polynomial or characteristic equation polynomial is s plus j root 3 and s minus j root. This particular route table is associated with the equation A. So s cube and s square will be having 1, 1 and 1, and this is your 21. So after completing this 1 into 1 minus 21 into 1 divided by 1, that is turns out to be minus 20. Then this one is your 0. Minus 20 to 21 minus 0 divided by minus 20, that turns out to be 21. So this completes the route table. Now let us try to find out about the stability of the rest of the system, which is denoted by your equation number A. Positive to positive means there is no sign change. Then again positive to negative, there exists one sign change, and then again minus to positive, that means there exists two sign change. So obviously we could comment that the rest of the system will be unstable one, and there are two roots that are actually lying in the right hand side of the S plane. So the two changes in the sign, the first column indicates the presence of two roots in the right hand plane and the system is unstable one. So on complete analysis of the system, we could say that there are three roots of equation A. The one root in the left hand side, that is s is equal to minus 3, and the two roots in the right hand side of the plane, that are s is equal to plus 1 plus minus j root 6. This is actually the complete solution of the equation number A. S cube plus s square plus s plus 21 is equal to 0. So these are the roots of this equation number A. So now close observing the complete roots, we can say that the system is stable one or unstable one. In this particular example, we could simply say that the system is your unstable one. This is your equation number A. S cube plus s square plus s plus 21, and s is equal to minus 3 and s is equal to plus 1 plus minus j root 3. These are the roots of this particular equation number A. So these are the applications of Raoult-Servais criteria. Raoult test only tests us whether or not a system is stable or unstable. We could simply say that a particular system is stable or unstable. It basically does not give any degree of stability. I mean, we could not say that any particular system is much stabler than the other system or not. It is simply telling us whether a given particular system is stable one or unstable one. It needs to have closed loop characteristic equation. It would be more convenient to work from open loop transfer function. These are actually the applications of Raoult-Servais criteria. These are the various references. Thank you very much for your patient listening.